And thank you everyone for coming virtually. I see familiar faces. It's nice to see people at least on Zoom. So this is based on joint work with Dale Kunin. Dale Kunin was a postdoc working with us at, in Japan at Okinawa Institute of Science and Technology. And he now went into industry. So he's now in a robotics company. So I hope you see my screen. So my screen is not my video, but rather slides and the board. So if you don't, please let me know.
That's great.
All right. So I'll start with some very basic things because it's kind of an intersection of complexity theory and topology. Let me say a little bit about both, which is very basic. Likely many of you find it very simple and know already. So many classical problems in low-dimensional topology, geometry, not theory, can be stated as decision problems. So decision problem is where you have yes/no answer, and an algorithm is a solution. And just a very basic question, say you have two manifolds. Are they homeomorphic? Yes, no. If yes, what's an algorithm? So in dimension 3, we will call this homeomorphism of three manifolds. And I will reserve capital letters for basically for calling the problems. So, and of course we have complements of nodes, usually in three sphere, but we can also look at them in arbitrary manifolds. And these give us three manifolds. So another related question is, given two diagrams of a knot, just projections of a knot or a link, of two links, are they isotopic? So we will call this problem link isotopy. So these are very, very basic problems at the core of knot theory in low-dimensional topology. But what happens is that whenever we look at similar core problems in two-dimensional topology, problems on surfaces, very often if you kind of search long enough, you find a paper saying there is a polynomial algorithm or there is a hope for polynomial algorithm. And obtain those algorithms can be very hard. However, in the end, you end up with something polynomial often. If you look at four manifolds and beyond, very often you end up having either problems that are undecidable or problems that are not known to be decidable. So a common example, if you just look at sphere recognition, two-sphere recognition is relatively simple. It can be done relatively, but if you have four-sphere recognition, you still don't know if it's decidable or not. And then beyond dimension 4, it's undecidable. And then three manifolds is a sweet spot where you have, on one hand, problems which are often still decidable. So you're often able to get an algorithm, but the algorithms are hard. So for example, homeomorphism of three manifolds is known to be decidable, but you have to use geometrization conjecture for it, geometrization theorem now. So we can actually discuss not just whether a problem can be solved or not, but also how hard it is. And what does it mean for a problem to be hard? Of course, we have many problems which are intuitively hard. We understand it, we try a long time, we can solve them, they're hard. But then you can restate the problem as decision problem and instead ask about its computational complexity. So is this decision problem computational hard? And just to remind, a very quick reminder of basic complexity classes, which I'm sure most of you know. And so NP is a set of decision problems where if you're given a yes answer and you're given a solution, which we call certificate, you can verify it in polynomial time. So it stands for non-deterministically polynomial, because if you have a non-deterministic Turing machine, the one which has more than one action prescribed on every step, then you can, with first action, guess a solution and then take polynomially many steps to verify it. But first step is non-deterministic, where you take a guess. And if your problem is an NP, it's an upper bound on complexity. It actually usually means the problem is kind of simple in terms of computational complexity, you do have exponential algorithm for it. And so one of the first examples in this area was set problem, satisfiability problem. So you have a Boolean expression and it's written only using and or not, and you have variables and clauses taken in parentheses. So here's an example of it, of just set formula. It's written in conjunctive normal form. That means you have these or inside and you have and between clauses. So one thing in parentheses is a clause. The question is there a variable assignment, so true, false to variables, that makes the expression true? So is the formula satisfiable? And to find such an assignment when you have a formula can be difficult, but of course when you have an assignment, to check it takes polynomial time in terms of input. So this is a classical example of a problem that is in NP. Another problem is called NPhard, if every problem in NP can be reduced in polynomial time to it. So these are problems that are at least as hard as all other problems in NP. So this is lower bound on complexity, NPhard. And actually a set problem is also known to be NPhard. This is Cook-Levin theorem. And on the intersection of NP and NPhard, we have a class called NP-complete, as you remember. So set problem was the first problem that was proved to be NP-complete by Cook and Levin independently in the 70s. And whenever we want to prove NP-hardness, we use some kind of reduction, something like Turing reduction. So one kind of Turing reduction is Karp reduction. So what you do, you take a problem A, which is known to be NP-hard, and then you set up an instance of a problem B that you want to prove to be NP-hard. And then you prove that an instance A has a solution if and only if the respective instance of B does. And that reduction must be polynomial. So given instance of problem A, it must take you polynomial time to construct an instance of problem B. And then you know that B is at least as hard as A. And that's what we will be doing. So very quick review of basics. Of course, the initial question is, we will look at NP-hard problems. It's a lower bound in complexity. Is it a good bound? And that's a tricky question. It's conditionally so. So conditionally, it's a good bound, meaning if P is not equal to NP, it's a good bound. So there are two pictures. Popular belief favors this picture. P is not NP, but you know it's a Millennium Prize problem. We still don't know. And if that is true, then you have this class of NP-hard problems where it is a lower bound of complexity. It is not polynomial. However, if P equals NP, then everything is NP-hard. And usually it is seen as the first sensible bound on complexity, lower bound. However, now conjecturally, people think that there are also some classes here between P and NP-hard. There is, for example, something called quasi-polynomials. It might be somewhere there, but again, it's conjectural. No one knows where exactly it is. So we will be talking about problems that are conditionally hard. All right, and please feel free to stop me anytime and ask me basic questions, because talking about it, I got both kind of basic questions, both about complexity theory and about knot theory, depending on what people know more. Despite that, in knot theory, we have very few polynomial algorithms. Very few problems were previously known to be NP-hard, previously meaning up to a couple of years ago. So let me quickly review what they are. Perhaps the first problem that was proven to be NP-hard was bound on a genus of a knot in a 3-manifold. So when I say genus of a knot, I don't really mean genus of a curve. What I mean is the minimal genus of a surface. So usually this is a Seifert surface. Most common definition says it's a connected, orientable, compact surface that's a knot bounds. You can also relax this and say your surface is disconnected, your surface is not orientable, but usually you prefer the first. And the surface must be embedded in three manifold, or you take a knot complement, and this surface must be incompressible. So again, if you're a topologist, you know what incompressible is. If you're not a topologist, then just think that this is a non-trivial surface. It actually interacts with a knot. It's not just a sphere. It's not just a torus hanging around somewhere without a knot. So I'll just show if this works. So here is a ciphered surface. This is, by the way, a software freely available online. I did not write it. So if you even take just a trefoil, these surfaces, there are many of them, and the way you formulate decision problem is, say, given genus G, can you find the surface of this genus? Minimal, is the minimal genus possible, is Z for your knot? And that can be tricky to figure out. So in general, it looks like a hard question to determine that. So that was proven to be NPhard. There is an interesting construction. First, it was done for a knot in an arbitrary manifold by Agol, Hess, and Lagarvius. And then, no, Thurston, I'm sorry, Agol, Hess, and Thurston. And then it was done for a link in S3. It was also proven to be NPhard. This is not an improvement. This is a different problem because instead of a knot, you have a link, but instead of a three manifold, you have a three. So you relax part of it and then you restrict a part of it. And also Lakenby took surfaces which are not orientable and not connected. So he called it not genus of a knot, but rather Thurston norm. And this is actually a very interesting reduction. And then another problem also Lakenby proved is a sublink problem. It's NPhard. So you're given two links and they're represented by their projections, so just diagrams. And the question is there a sublink of one isotopic to another link? And this paper actually kind of inspired our work because what Lakenby argued himself, he said, you know, these problems are very interesting problems, but maybe they're not the most natural and core problems in knot theory. And there are problems that we think much more about in knot theory. So why don't we try to prove that those problems are NP-hard? Because intuitively they seem to be hard.
Can you say one word about what complexity problem this gets reduced to show the hardness?
Sublink?
Any one of them, yeah.
Let me remember. I think, if I remember correctly, bound on a genus is set, if I remember correctly. So they construct a surface. And then sublink, I think it's actually, again, if I remember correctly, it's Hamiltonian path problem on graphs. So somehow most reductions end up being to a few basic problems like Hamiltonian's path or set, or it might be some restrictions of set because set has several versions. So, and so if we, again, what Lakenby argued is that there are maybe more core problems in that theory, and we should try to prove that those are NP-hard as well, because it looks like they will be. One of them is homeomorphism of three manifolds, or if you look at link isotopy, so we know that links are knots, knots are determined by their complements in three sphere due to Gordon-Luke theorem. So you have isotopic knots if and only if you have homeomorphic knot complements in three sphere. For links, this is not exactly so because you might have links with the same homeomorphic complements. However, we know which exactly links are these. We know how they look like. So kind of, let's say, class.
How does one specify a three manifold?
Do you mean how do you give it as an input?
Yes.
So one thing you can do for links, you can just give it as a diagram. And there is a way to decode the diagram called Doker-Thistlethwaite code. So you can just put in Doker-Thistlethwaite code, which tells you where crossings are. And then Another way is to give it using a triangulation, but when you're working with various software, very often you just have something called census, like a table of manifolds, where you already know which manifold is which, and you just operate certain kind of names. But
when you say that homeomorphisms of three manifolds is hard, which model, which presentation of that is that?
So for example, you're given three manifolds and they're triangulation.
Okay.
So I think this is, if you look at Greg Kuperberg's paper, he actually gives algorithm for it. And algorithms use a lot of big tools like geometrization theorem. And I think he starts with a triangulation and then topological triangulation, and then we go on.
But by bound only is an upper bound, right?
So let me talk about it. So what happens is actually lower bound, I believe. So homeomorphism of three manifolds, we know it to be computable because we have an algorithm. And actually Greg Kuperberg proved that it's in certain class for an upper bound called elementary recursive. So it's a tower of exponentials. But lower bound is still a big question because it looks hard. It looks like the algorithm is hard. But so far, the only known result is by Lackenby, where he proves that it's at least as hard as graph isomorphism. And then a question appears how hard graph isomorphism is, which is very historically kind of old and very hard question in graph theory and in complexity theory. So as far as I know, the most recent result is by Babai, a breakthrough really, where he says that there is a quasi-polynomial algorithm. So for our purposes, this would be a lower bound, which is 2 to the O of log n to the C. So this is, again, whether this can be polynomial, whether this can be NP-hard, we don't know. Current belief is that this lies somewhere between P and NP-hard, but really no one knows. So conjecturally, it's some kind of intermediate complexity between P and NP-hard, but again, we don't really know. So, and that's what we know for lower bounds about homeomorphism of three manifolds. So it would be wonderful to actually prove that it's NP-hard, but no one was able so far. And it looks like it might be. And then a very recent result where I've seen preprint just, I think this year, is link crossing number, another very natural problem by Dennis May, Schaffer, and Sedgwick. So given a link represented by a link diagram and a natural number, does this link have a diagram with M crossings? Or is it equivalent to a link with most M crossings? And I should say, whenever in these decision problems you say at most M, you can also say, is it equal to M? These are different problems, but if one is NP-hard, another is NP-hard. Because you can take one as an oracle and basically call one and get it another as NP-hard as well. So these are two maybe more natural problems which were recently proven to be not NP-hard, but at least some lower bounds. Homeomorphism is as hard as graph isomorphism at least, and link crossing is NP-hard. And I'll also mention there was a result about 4 manifolds invariants for links by Dennis May, Rick, Sedgwick, and Tanser. And then let me maybe talk about the problems that after reading this Lackenby's paper, we found to be very natural, very interesting, that we wanted to prove to be NP-hard. Right. So, well, first of all, let's go to link isotopy. There are link equivalence. There are many ways to look at link equivalence, and perhaps the oldest is to look at Reidemeister moves. So back in 1927, Reidemeister proves that any two diagrams of a knot can be taken one to another by a sequence of 3 simple diagrammatic moves. Right? So you have Reidemeister move 1, where you just remove a loop or add a loop. You have Reidemeister move 2, where you just move a strand lying above another strand away. And then you have Reidemeister move 3, where you have a crossing and you slide a strand above this crossing past it. So what it means is that whenever you have ambient isotopy between things, between links, you also have equivalence that is achieved by doing these moves on the plane to their projections plus planar isotopy. So ambient isotopy is pretty much the same. He proved as planar isotopy and these moves together in some sequence. And then you can ask, instead of just link equivalence in general, you can say, okay, link equivalence by Rademacher moves problem, given two link diagrams and an integer k, are the diagrams related by a sequence of at most k Rademacher moves? And first of all, of course, if it's a decision problem, we give k, but in general, as a mathematical problem, this kind of k has been a subject of significant research. There have been a lot of work done on the bounds, upper bounds for the number of Rademacher moves needed. For example, there has been first work was by Haas, Lagarius, and Peipinger. What you have number of crossings of the diagram, and you ask how many moves are needed to unknot it if it's an unknot diagram. What's the upper bound in terms of number of crossings? And they gave exponential upper bound in terms of number of crossings on the number of moves needed to unknot the diagram. And then Hayashi gave a bound for splitting a link. So splitting means taking its component apart if they're not really linked together. And then there also was work by Covert-Luckenby and Luckenby about unknotting, and Luckenby got polynomial upper bound, and it has some kind of crazy power. I don't remember now, but very big number in the power, but the base is n, so it's polynomial in n, where n is number of crossings, and there's upper bound on the number of moves. And but a caveat is that we still don't know whether the problem is in NP. So you might think about this as let's get some kind of simple certificate like K diagrams, for example. So maybe it's worth saying here, what is the size of input? So when you have such a problem, your size of input is, on one hand, you have number of crossings, and this is for the first diagram. So you're given two diagrams, and you have number of crossings for the second diagram. And then you have this integer k. So it takes actually log k to give integer k to a computer. And so if you, for example, try to say my certificate is k diagrams between one link and another link, it won't be a polynomial certificate. It will be exponential in terms of log k. Therefore, you have to be careful with what your certificate is. But you can say that my certificate is my moves. I can specify what my moves, Rademacher moves are, and where are they. And then if you have polynomially many moves in terms of n, that would be a good certificate. So polynomially many Rademacher moves in terms of n1 and 2 would be a polynomial certificate. However, we don't have that polynomial certificate. So the bound that we have is only for unknotting. Luckenby actually announced another result where he says that there is a polynomial upper bound for arbitrary link, getting one diagram to another. However, the polynomial will be dependent on the link. So we don't have, even that is not yet published, but even if it is, it looks like it won't be a universal polynomial bound for all links anyway. And therefore, we don't have polynomial certificate for this problem. That looks like a hard problem. So we don't have it an NP. But then, of course, the question is about lower bound. How hard it is, can we prove that it's hard enough? And so that's something we proved, and there were two teams working independently on this. We didn't know. Together with Dale, we worked on this, but also Demis, Meirik, and Sedgwick and Tensor worked on this. And we proved that a seemingly easier problem, which is unlinking by radiomaster moves, is NP-hard. And then if you prove that an easier problem, which is a restriction of your harder problem, is NP-hard, then your harder problem is also NP-hard. So this implies that link equivalence by radiomaster moves is NP-hard. And Demis, Meirik, and Sedgwick and Tensor improved it even further. They showed that an even easier problem, which is unknotting, so you restrict your link to just having one component, just being a knot, unknotting by radiomaster moves is NP-hard. So that implies that unlinking by radiomaster moves and link equivalence by radiomaster moves is NP-hard. I don't have maybe now time to do this because I want to talk about other problems, but unlinking by radiomaster moves, the proof was kind of an example of how a silly idea gets you something interesting, because really we just took a very simple link and showed how we can put to every Hamiltonian path problem, we can put in correspondence such a link. And basically the proof is something like one paragraph. So it takes you a long time to kind of find these reductions, but when you find how to reduce it, when you get the idea, often it's a very neat and short proof. And but I want to talk about some other problems also that seem quite natural in knot theory. And seem quite hard. So one set of problems is about unknotting and unlinking. So there's a notion of crossing change. Basically, you have a diagram where you have overpass, underpass, a crossing, and what you do, you just substitute your diagram one crossing with this. So, for example, you have a figure 8 knot. Let me see. Say, and you just take one crossing and you substitute it. And then instead you would have this, and very quickly you would arrive to an unknot. Let me see, I didn't go. So if I just substitute one overpass to one underpass, very quickly I will get something completely unknotted. So, and then here you see this is figure 8. And this is unknot. You just kind of pull this down and then you untwist things. Kind of. So we'll get a diagram of a circle. And what this means is that unknotting number of figure 8 is 1. So you can do just one crossing change and unknot figure 8. However, definition of unknotting number says that this is the number of crossing changes required to arrive to an unknot diagram minimized over all diagrams of the knot. So what it means is that if, for example, I had 2 changes here to do, I could not have stated that this is has unknotting number 2 because maybe there is another diagram where I only need one crossing change. So the fact that you have to minimize it over all diagrams, of which there are infinitely many, makes unknotting number very hard to find. Unlinking number is something similar when you have not knots, but links with several components. And splitting number is something similar where you try to just split components from each other. Make them disjoint, disconnected. And for unnotching number, we actually don't know yet that it is even computable. There is no algorithm for it. So it really looks like a hard problem. And there has been a huge number of work on this. Maybe let me say a bit about prior work just to justify that it's really a hard problem. So prior work.
Nasha, I have a question.
Yeah.
I seem to remember this result of Lackenby's where you could take two components of a link, and with polynomially many moves you could put them distantly, just completely separate them from each other.
Split.
Yeah.
This upper bound on the number.
That was like a polynomial. So I mean, how does that fit with this?
But that's not about unnotching. That's about Reidemeister moves, right?
Oh, I see. Oh, I see. I'm sorry. All these are for the unknotting.
Right.
Gotcha. Okay.
So you could ask, it's also a decision problem. The question would be how, given a link diagram, which is a split link, and given a number k, can you split it in k Reidemeister moves? And then maybe like in this work would provide a polynomial certificate for you. So the problem would be in NP. If the polynomial is independent of the link, if it only depends on the number of crossings. And if it's an NP, then hopefully it's a relatively easy problem. But again, we should double check if the polynomial is independent on the link. And then, and here, rather than Reidemeister moves, so Reidemeister moves correspond to isotopy, and unknotting these crossing changes, they do not. You completely change your link or not, right? So you change your curve. And what was done on unknotching before, so there was a lot of work. However, usually these are kind of partial results, which are still very hard to obtain. So you obtain lower bounds on unnotching number. And really, as far as I know, most of those bounds, except for I think one particular result, they all equal to 1. So you say that your lower bound is 1. So all you're able to prove is that unknotching number is not 1. So there is one result for torus links, which says what exactly unlinking number is, which depends on P and Q in torus link definition. P and Q is how many times you wind around the torus this way and that way, along longitude and meridian. But this is the result where you have not 1. Other than that, you're usually just happy to say that it's bigger than 1. And that's actually hard to say because you're saying that no matter what diagram you take, you can't do it with just one crossing change. And for example, back in 81, Nakanishi published a partial list of unknotching numbers. So he did it computationally, or partially, with a lot of course mathematics, partial list of unknotching numbers for knots with at most 9 crossings. And then people really tried, even for knots with at most 9 crossings, people tried to understand what unknotching numbers are for those which are not in the list. So for example, there is Licorice paper from 82, where he takes just one particular knot, 7-4, and he says that unknotching number is 2, so unknotching number is not 1. And a bunch of techniques has been used for this. For example, there are papers using gauge theory, and there are papers using Hilgard-Floor homology for this successfully to get unknotching numbers for some particular knots. But in general, it's something hard to determine. So all this kind of hints to the fact that perhaps it is at least an NPhard problem. But that's something we were not able to prove, so that's still not known. And we still don't know any upper bounds and any lower bounds about Unnotching number problem, if it's formulated as a decision problem. So that's something we looked at. Instead, we proved that unlinking number is NP-hard. So this is for links, and splitting number is NP-hard. And for linking number, there is also alternative proof by Demis-Meyrick Sedgwick tensor. And I'll talk about this a bit if I have time. I'll talk about the proofs, about the reductions. And we based it on another proof of a simpler, maybe not as interesting, but useful problem called unlink as a sublink. So whether you have a non-component unlink as a sublink of a certain link. So if I have time, I'll show you the reductions today. But that's a very natural set of questions, and just to maybe advertise it more, this problem, Unnotching number still has neither lower nor upper bounds. I would be super excited to see one. There has been a recent breakthrough, I think, in a way, but again, not about unnotching problem, but only about unlinking and splitting by Lackenby, and about upper bound. And what he proved is that the problem, oops, I'm sorry. So the problem is splitting number equals to 1 is unlinking number equals to 1. These kinds of problems are computable. So there is an algorithm, and it's not even for all links, but for, let's say, many links. So for links satisfying a bunch of restrictions. So that's as much as we know about upper bounds. But hopefully I'll show you today that both these problems have lower bounds being NP-hard. And then another set of problems which also sort of interest me and which is not completely solved concerns alternating links and knots. So a knot or link is alternating if there is a minimal crossing diagram such that overpasses and underpasses alternate as you travel along. So for example, you go here, you have over, under, over, etc. So these are all alternating knots. And so given a link or a knot diagram, is a link or not alternating? This looks like a hard problem. It looks like it's hard to determine, but we don't have any lower bounds. Very recently, we got an upper bound. There was also, in a way, a breakthrough work because for a very long time, people tried to understand what's so special about alternating links. There is a bunch of results about nice properties. They have nice Jones polynomials, nice geometry, nice topology, nice triangulations. Some of it conjecturally, some of it has been proven, but what exactly makes them so special? And there have been results maybe partially explaining certain special things about their geometry and topology. This was independently by Howe and Green, Juhas, Lackenby. So you have a certain pair of very, very nice surfaces embedded there. And using that pair, you can actually determine whether a link is alternating. You can detect that pair of surfaces. This gives you exponential algorithm, tower of exponentials, but still it's computable now, decidable, but we don't know any lower bounds. So it looks like it's an NP-hard problem. And we were not able to prove that it's NP-hard. Instead, we took another problem, which we were able to do. This is alternating sublink, also was not known. So given a link diagram and an integer k, does the link contain a k component alternating sublink? So we prove that it's NP-hard with Dale. I won't show the proof, but it's a reduction to set. So, and before I go and try to show you some ideas for the proofs, feel free to ask me any questions on all this. At least by now, kind of hopefully know what problems I'm talking about. Very general motivation for this.
Is it known, like in factoring, that a quantum computer could make anything faster, yeah?
Quantum computer could make.
So factoring can be done. I mean, I believe factoring is easy, but nobody knows that. But factoring can be done quickly if you had a quantum computer. I'm sure people have asked whether a quantum computer would allow you to handle some of these problems. Is there any class which it would succumb to a quantum computer known by kind of a Shor algorithm? Nothing like that, no?
No, I have never seen anyone asking it or looking at it. So very often the algorithms involve triangulations and something called norm.
I'm sure that would only apply to something that's not NP-hard, of course, but that's something that you might not know is polynomial, but that looks like it's polynomial, and with a quantum computer might then be provably polynomial. So like factoring.
Yeah, I don't know. So most algorithms, so whenever you work with homeomorphism or detecting surfaces, what you do normal surface theory usually. So you have a triangulation and you have surfaces that you put in normal position, so they intersect tetrahedron nicely. And then you often have to solve certain systems of equations. It's like linear programming and construct those surfaces. And usually you get a tower of exponentials there. And I don't know if this can be helped by quantum or not. All right, so before I go to proofs, and I want to show unlinking and splitting reductions, let me maybe show you kind of random, but you later see not so random fact from knot theory. So you see a picture of something called Perunian link. This is a non-trivial link. However, if I remove any of its components, any color I take away, I will have an unlink. So I will have just separated disjoint circles up to isotopy. So such links are well studied. There are many examples of them. This is just one of them. So I remove yellow, but also I remove pink, red, orange, green, blue, any one, and then I have just disjoint circles up to isotopy. And any link with such property is called a Perunian link, and I will be using them in the construction. So first of all, first problem, maybe it's not such an interesting problem by itself, but it will help me to build up to unlinking and splitting number problems. This is unlink as a sublink. So given a diagram for a link and given a positive integer, k, is there a k component sublink of our link? That is an unlink. So basically I just want k disjoint circles there. Do I have k disjoint circles there? Can I erase a part of a link and get k disjoint circles up to isotopy? And it actually doesn't look like such a hard problem, but turns out it is NP-hard. It's actually NP-complete because you can get polynomial certificate just by taking the sublink itself and check if it's an unlink. So we will perform a Karp reduction to three-set satisfiability. This is a set problem, but you limit every clause to 3 variables. And what we will do, we will take a formula with n variables, and for each variable, we will take a Hopf-link. So Hopf-link is what you see here. This is just one Hopf-link. And so you take n of them for each variable, and you label components, upper components by variable x1 and lower by not x1, etc. xi, not xi. And now I want to add components that correspond to clauses. I have m clauses, so m parentheses, pairs of parentheses with expressions. So what I will do, I will zoom on this little frame. And if I zoom on this frame, that's what I see. That is my zoomed in frame. So that's kind of one Hopf-link, these 4, this and this is one Hopf-link, second Hopf-link, etc. And I will add Perunian components to it. To add Perunian components, actually, I will do it so that every component corresponds to an iterated commutator. So there is a commutator inside the commutator. And when I do this, I write this commutator so that it corresponds to a clause. So here I have a clause. So I put not x3 and x4 inside the first commutator, and then not x1 outside in the second commutator. And then if I open it up, I have an expression and how I construct my link. If I have not x1 there, then I go under not x1 strand. And then if I have not x3 there, I go under not x3 strand. And I go above everything else. If I do x4 there, I go under x4 strand. And first I'm going in that direction. But once I start having negative power, I still go under, but in the opposite direction. So not x3 to the, not x3 inverse means I still go under, but now in the opposite direction, in this direction. So that's really a very simple kind of procedure to construct a link component. And it was described, I think, by Dale Rolfson, maybe. Well, he doesn't exactly says anything in that detail, but he kind of has a picture in his not theory textbook. And what happens now is that so this is Perunian. So whenever you have, say, not x1, not x3, x4, and this component, you just remove one of these four things and you get just disjoint circles. So if I remove this, or I remove this, or I remove this component, or I remove this thing itself, I get disjoint links. If I do not look at the rest, I just ignore the rest for now. And what I will do, I will, for an assignment of true and false, or zeros and ones for f, whenever I have x1 assigned true, x1 assigned 1, I will just remove it. I will just erase it from the picture. And that will actually give me an unlink. So I will actually get that f is satisfiable if and only if there is an n plus m component unlink. And indeed, so once you delete once, you see every clause has at least one true assignment. So for every clause, I will have one component to delete. So for every sublink of 4 components, where I have, say, not x1, not x3, not x4, and this Perunian thing, one of them is 1. So I delete 1, so I have unlinked links, unlinks. And then in the opposite direction, what I have is that if I want an n plus m component unlink sublink, then on one hand, it must contain every Perunian component, each of these guys, because there are m of them, and it must contain a component, one component from each hop link, because there are n of them. I need to take n from somewhere. So basically, I will take all these Perunian components and I will take one of each, either this or this, when I construct my n plus m sublink. And that will give me an assignment for the formula. So if it participates in my formula, I assign it 0, I assign false. And if it doesn't, in my unlink, if it doesn't, then I assign 1. So basically what happens, you have just enough components to have this n plus m component unlink by taking all Perunian ones and one of each hop link. And that is equivalent to an assignment of zeros and ones, where x1, not x1 have opposite assignments, and each clause has something that makes it true. So formula is satisfiable. So it's it's kind of easy construction, and it's a polynomial construction, because given a formula, it takes you polynomially many steps to construct a link. So this gives you polynomial reduction to 3 set, and then you can say that Unlink as a sublink is NPhard. And again, maybe when I say this fast, you think like you have to sit down and write it down, but the idea is really, really simple. And now I'd like to build up on that to show unlinking number. So again, we take number of crossing changes that makes a link and unlink, but we have to minimize it over all diagrams. The problem sounds as follows. Given a link diagram and given an integer n, does the link have unlinking number n? So what I will do, I will take the previous proof, and instead of hopflink, instead of every instance of hopflink, I will do this whitehead doubled hopflink. So you see I kind of doubled it, and there is this element. So what happens if you just take one of these on its own? If you just take kind of, am I doing this right? If you just take this, this is actually an unknot. So by itself, it's an unknot. But if you have two of them together, then it's a link, it's linked. You can't just take it away. Because here I could just slide it down and just get this. And however, if you have this kind of picture, you can do something that we will call unclasping. You can just change one crossing here. You can change it to this crossing over to under. And that will actually break off the whole structure. That will leave you with just two unknots like this. So just one crossing change, which we will call unclasping, will leave you with unlinked unknots. And we have to prove that the new link where I substituted, I took previous link with all those Perunian components and hop links, I substituted everything by whitehead doubles. And I want to prove that the new link is unlinked in exactly n crossing changes, if and only if the formula is satisfiable. And the problem here, maybe it's actually not so hard to prove for this diagram, kind of follow the previous proof, but what happens, you have to prove that you can do it in no less than n crossing changes in an arbitrary diagram. So you have to show that your proof is independent of this particular diagram. And what we did for that, we introduced something called unlinking moves. So these are just homotopy moves. You have a link and you have this arc alpha, and you change your link by taking your strand and kind of putting it, wrapping it around the other strand, weaving it around. And this move is determined by an arc alpha. And you can reformulate now unlinking problem, saying that this is the smallest number of unlinking moves needed to change the link into unlink. And indeed, clearly this corresponds to crossing change if you do unlinking move. And what you can do if you have all these unlinking moves, you can just isotope your diagram so that your arcs like alpha are perpendicular to the projection plane. And then every unlinking move will be just like a cross under a crossing. So this will be just a crossing change. And we will operate with those instead of crossing changes because they are independent of the diagram. And maybe I'll take a couple of minutes to tell you about the lemma, just to point out what's subtle here, why we go into all this trouble. So what happens, in that first diagram, which I had of whitehead doubles, I could do an unlinking moves, and I could prove that it's unlinked in exactly n unlinking moves by unclasping those whitehead doubles if and only if formula F is satisfiable. However, now I want to take any diagram, arbitrary diagram, and say that it's still true. And what I will do, I will say, okay, there is another diagram, and I have another sequence of unlinking moves. I don't know what they are. I don't know how my diagram looks. But what I can do, I can substitute them with a sequence of moves that just do unclasping of those whitehead doubles and only get shorter sequence of moves. So once again, I know that in that first initial diagram, and I'll go back a bit, in that very first diagram with all those whitehead doubles like here, I can do n unlinking moves, and my diagram will be unlinked if and only if my formula is satisfiable. I will just mimic the proof of the unlink as a sublink problem, but I don't know what happens in an arbitrary diagram. So when I take an arbitrary diagram, I say, okay, maybe there is another sequence of unlinking moves. But I claim that I can substitute it with moves that unclasp those whitehead double hop links. And when I substitute them, I only kind of get better. I get shorter sequence of moves. For that, we use this lemma. So lemma has long formulation, so let me maybe read it. But basically, it allows you to substitute any sequence in any diagram by that particular unclasping sequence of moves. Unclasping moves sequence. So what it tells you is that if you have a link and you have a component, here's K of a link, where at least one of your unlinking moves just separates K from the rest, just kind of puts K aside somewhere, and involves K. And then what you can do, you can replace this sequence by a sequence where you would still put K aside and you would still get the same result as you did before, but you would do it first. You would put K aside first, and then you would do all your moves and get the same result in the end. And when I say it, it maybe almost sounds like a tautology, like I'm saying the same thing, if then the same is true. But it's a bit subtle because, for example, if I try to separate K and I don't kind of move it away, and then I do this crossing change that does not involve K directly, I can still link K back. So I have to make sure that all my moves that do not involve K, they also kind of do not involve this disk K bounds. So you can kind of split one component. However, you can do moves completely not involving that component and still kind of link it back. So we prove that you can avoid that. That you can just, by one move, you can kind of split your component, set it aside, work with the rest, and still get the same result as you did before. So this is kind of, we compartmentalize our sequence. See, part of the sequence does this, and then part of the sequence does this. And using this lemma, what we do, we take a sequence of unlinking moves that makes our link and unlink. And this is in an arbitrary diagram. But then we know that for every double hop link, no matter how it looks, no matter how the diagrams looks, there is a move involving only these components, because you can't unlink this link otherwise. You can't unlink it by doing some other things. You have to do this move eventually. And so we say, okay, let's substitute it by unclasping that thing first, and then doing the rest of things. And then we apply the lemma again and say, okay, unclasp the second link and kind of set it away and do the rest of things. And then again, we substitute our sequence. So we unclasp the third hop link, set it aside, and do the rest of the things. And the lemma tells us that the resultant sequence in the end only either shorter than what we started with, or is the same length. So, and you still have to unclasp all n of them. So you have exactly n unlinking moves. So again, there is a bit of subtlety, which I remember we first drew pictures and it's almost like it must be obvious, but because you're working with an arbitrary diagram, you have to make sure that nothing strange happens in that other diagram. And I think I want to be talking about split because I don't have enough time, but basically the idea is similar. You just, instead of hop flinks, you take disjoint whitehead doubles, like on this picture. You label them with X1 and not X1. You still draw Perunian components somewhere here, like we did before. And you take an extra component, this one, joining them, because you don't want to split your link too soon. And you take its end cable. Because you don't want your link to be split in less than n crossing changes. And then you do something actually quite similar. So I'll stop here. It's really, in a way, it's a really simple idea, but then of course, when you start writing it down, you have to take care of all these things. Thank you.
Well, that was very nice. Thank you very much.
Thank you.
We have a few minutes for some questions.
Could you repeat the statement of this last theorem that you're proving, or that's kind of theorem?
About the splitting.
Yeah. What is the theorem?
So if you formulate a splitting problem, do you have it here? Splitting number. So given a link diagram and an integer n, does the link have splitting number n?
Mm-hmm.
This decision problem will prove that this is NPhard.
Okay. So my question is, amongst most of these problems are NPhard, and you're showing that, and some you expect to be and maybe are not shown. And then you mentioned one result of Lakenby, which was a very restricted problem where he could do something in polynomial time. How do we tell? I'm just asking for the intuition. It seems to me like almost any of these problems should be NP-hard, right?
Wait, so Lakenby looked at homeomorphism of three manifolds, and it also looks like it should be NP-hard. It's just that he was not able to prove it.
But you had another problem where you restricted two numbers to be one. And then you said he had a polynomial time. In other words...
oh, no, that's a polynomial. It's not a polynomial algorithm. So that's polynomial bound on the Reidemeister moves.
Oh, okay.
It only tells
you know, so linear programming is remarkably in P, right? So that's kind of one of the most important things that are in P. Is there anything here that's kind of remarkably in P? That's my question.
I don't know anything that looks hard and has a polynomial algorithm. Is this what you're asking about?
Yeah, so I'm kind of asking you, is everything supposed to be NP-hard?
NP-hard, I think. At least I don't know. So again, what maybe the first motivation is that there are very few polynomial algorithms known.
Okay. Yeah, that's true overall, but linear programming sort of sticks out. And
right, but even, you know, for this diagram...
Convex programming, yeah.
Right, for diagrammatic problems like unlinking, unknotting, we're not using normal surfaces. We're not using linear programming. However, still we don't have any polynomial algorithms. So somehow dimension 3, with 3 manifolds, you have very little. I looked into various problems on surfaces, and I looked into various problems on 4 manifolds, just kind of superficially looked. And for surfaces, you do have a bunch of polynomial algorithms doing things. And then for 4 manifolds, it's like you don't even know what's there. You don't even know if things are computable. So I would expect they're NP-hard, but I would expect that they're even harder for 4 manifolds, many basic problems.
Mm-hmm. Okay. I was sort of hoping like something like factoring, which, as I said, was supposed to be easy, and that's easy here. Something that you could say, look, this is remarkably polynomial.
Yeah, I don't know anything.
I've always found the theorems which show things are fast much more interesting than the theorems which say that they are NP-hard, personally. So like, you know, Tarjan in his youth showed many things are polynomial.
Right. So if you look at software, for example, on 3 manifolds, all of it has exponential algorithms, and people use heuristics. So a lot of them do not use actual algorithms, but use procedures. So they are not strictly algorithmic because they want to make it fast instead of, doing tower of exponentials. So whereas heuristic ways to speed it up in practice, but very often what underlies there is mathematically exponential, or usually even a tower of exponentials. Like, for example, computing hyperbolic structure would be, it's a procedure, but there are exponential involves, or working with normal surfaces is tower of exponentials.
Could you repeat what about hyperbolic structure? I was about to ask that.
So hyperbolic structure, well, if you want an algorithm that tells you whether two manifolds are homeomorphic, you can get a strict algorithm. For example, Greg Kuperberg does it in his paper, and it involves, for hyperbolic manifolds, it involves hyperbolic structure. It involves equations and looking at the hyperbolic structure, and it's a tower of exponentials. But if you compute it in practice, for example, SNAPy, it's a procedure. It's not strictly algorithmic because it recomputes some things, and there is some heuristic involves. And the reason for this, because it's written so that it works fast in practice. You wanted to compute things very fast. And procedure in this case is something that helps you to do this. The same if you look, there is Australian rating software, for example, Ben Burton wrote Regina and other things. So everything is exponential, but they have shortcuts. And these are procedural shortcuts. Often they're heuristic, but these shortcuts help program run fast, right? Having exponential algorithms. So I would be very interested in seeing anything, for example, saying anything about Unnotching number, which is something like a very basic problem. It's been around for a long time and we still don't know, is it hard, is it easy? Likely it's hard, but we don't even know if it's computable. And at the same time, we can't prove that it's NP-hard.